Welcome all to another session on line commutated and PWM rectifier course. And in today's discussion, we are going to talk about dual active bridge or DAB converters. So, looking into the course content, we can see that we are now in the 11th week in which we are talking about these AC-DC converters for EV chargers. And in this one of the most important topologies under this one is the DAB, which we are going to talk in details today. And um, it is considered to be as one of the most important converter for all future applications in EV charging. So we will first talk about the application areas in which we'll talk about it, and then we have we'll understand why this DAB is getting popular, and then we will talk in details about the understanding the DAB operation and the soft switching part, and at the end we will show you some simulation results and some of the experimental prototypes that we have here in our labs. Okay. Um, now, the dual active bridge, the dual active bridge DAB converter, as it is known, this is one of the, it is an isolated, the most promising isolated DC-DC converters. And the power ranges can be from several kilowatts to tens of kilowatts or even higher. Okay, with silicon carbide devices. Okay, DABs we have seen in literature, like in research literatures, 100 kilowatt or even more than that. Okay, so this is like a high powered converter, uh, but there are two ports, usually like one high voltage port and a low voltage port. Okay, so if we think of from like an electric vehicle charging point of view, the battery will be at the low voltage port. Okay, so this will be the battery. Here the battery will come, and here the grid will come. Okay, but remember, this converter is a DC to DC converter. Okay, so there will be an AC stage which is before the DC stage. Okay, and that must be kept in mind. The power, this is like this value is kind of like constantly getting updated. So this value is uh, every now and then we see that a higher value of DAB getting reported, and the switching frequency is like in this range. So if we take it, so this is the converter inside. I will talk about it in details. But if we take it as a black box, basically there is one input DC and there is one output DC. Okay, we understand this one. And it basically has inside there is a transformer. Okay, and so this is a isolated DC-DC converter. The second important point about this converter is that it allows bidirectional power flow. So which means the energy can flow in both the directions. Okay, so this is another important property. So you can charge the battery from the grid, but you can also discharge the battery into the grid or into any other vehicle. Okay, so for example, suppose we have seen there are applications which we sell, which we say G2V and V2G. Okay, this kind of names are getting popular. G2V means grid to vehicle, and V2G means vehicle to grid. So in certain situations, it may be advantageous to use the power from the battery of the vehicle and put it into the grid so as to support the grid. Suppose the grid is not present, then it is possible to actually support the grid, or kind of like to form a local grid, okay, a household supply, if the battery is there from inside the electric vehicle. So this bidirectional power flow is possible, okay, with this converter. Next important point is the soft switching, and we will talk about it here, and we will introduce what is soft switching. Soft switching means a kind of switching in which the switches switch either at zero voltage or at zero current. Okay, and thereby when it does that, the loss which is going to happen, the switching loss goes to zero or very close to zero. And this is why it is called the soft switching. We have seen earlier where the when a switch switches, like a MOSFET or an IGBT, when it switches, if the voltage across it is the VDC and if the current is I, and if it goes to zero, then it is called the hard switching. Okay, so these are the two terms which are frequently used in power electronics. Hard switching is the conventional way of switching, but soft switching means that when the switch is switching, either the voltage or the current through that switch is zero. Okay, so we'll see that this is happening in the DAB. DAB is also modular, okay, which means that the DAB can be used as a building block for larger converters. Okay, we will see this in a few slides from now, where this DAB will be used as a building block to connect to the medium voltage. And it has a good efficiency, okay. And very often we see that the DAB with an efficiency of more than 97% has been reported with the silicon carbide devices. Okay. So here you can see where a DAB can be used. Okay. For example, here we have the grid and here we have the rectifier. Okay. And this rectifier can be a bidirectional rectifier or an unidirectional rectifier. And then, so if it is like a three-phase, then we form the DC grid here. And from that DC grid, you can see that we can charge an electric vehicle, we can have a battery storage systems like that, okay, where the DAB can be used. Very, very important application. Okay, and you can see here also the DAB can be part of a single phase application also. Here, this AC to DC, we have seen a lot of such converters here, right? We have seen the boost PFC. We have also seen the totem pole PFC and all those stuff. So it can be here, okay, and the first stage. And then you have the DC link, right? Here is the DC link. And then you can have the DC-DC converter. Okay, here you can see the DAB is acting as a DC-DC converter here, and here is the battery here. So you can see here that the input voltage here on the capacitor is like a, DC with an AC ripple. Okay, that also we will see how does it come and why it is coming. Okay, but the DAB, as I was pointing out in the previous slide, the DAB can be used as a building block for like a higher voltage. And here we can see one such application. Here you can see that there is a high or medium voltage um, grid here, and then we have an AC to DC converter, okay, and then we have a DC DC converter. Okay, this is where the DAB comes in. Okay, and an actual implementation you can see here. This is the AC to DC converter, and then you have a DC DC converter, and the outputs of these DC DC converters is connected in parallel. So from a medium or high voltage, okay, medium voltage or high voltage, we can get a low voltage, high current application. Okay, so this DAB can be used as a building block. Okay, so this also is uh, the way by which we make the solid state transformer, okay, or smart transformer, SST, solid state transformer. So DAB is basically can be used as a building block in a solid state transformer also, okay, where the input voltage, the medium voltage or the high voltage, you can see here 13.8 kV. But here the low voltage DC bus is like 1.3 kV, 1.2 kV, like that. So it is high voltage to low voltage part of that conversion. Okay, fine. So these are some of the application areas of the DAB. And with this understanding, let us now go into the understanding, or let us now understand like how the DAB operates, right? Now, in a DAB or a dual active bridge, so this is the dual active bridge. The name itself says that there are two active bridges, and you can see here, this is one active bridge or one H bridge, and there is another H bridge. Okay, and now here we have we have four controllable switches here. These are usually all made up of MOSFETs, and in present generation, these are all silicon carbide MOSFETs, right? Of course, instead of MOSFETs, you can use also diodes, but then it becomes an unidirectional converter. And variants of these, like phase shift full bridge and others, can be derived from the dual active bridge principles. Okay, now apart from these two H bridges, we can see that there is a transformer, okay, which has this 1:n ratio. And there is also this inductor. Okay, the inductor is very important for the operation of the dual active bridge. Okay, sometimes people use this inductor as part of the leakage inductance of the transformer. Okay, but most of the time, research has shown that a separate inductor apart from the transformer is necessary for a proper control of the DAB. So generally, we put a separate inductor along with a transformer, although theoretically it is possible to have a single transformer where the leakage inductance of the transformer can take up the role of the inductor. But usually, generally, this is avoided, and we have one inductor and one transformer separately. Of course, you have these two DC sources on the both sides. Okay. Now, we already know how these H bridges operate. We have seen this several times in the course now. And so we can understand that between these 2 points, okay, you can have a controllable voltage source here. Now note that here uh, we will use square waves, okay, or quasi-square waves. Why? Because if you turn on these switches S1 and S4, then you can get this voltage. And if you turn on S1 and S3 or S2 and S4, then you get a zero voltage here. And if you turn on S2 and S4, then you get a negative voltage here, right? With respect to the fictitious midpoint of the DC bus. So you can get a quasi-square wave or a square wave in these 2 points A and B. Okay, and this voltage VAB, if I say this one as VAB voltage, this voltage is fully controllable because in a sense that how we turn on the MOSFETs, right? So a controllable voltage, square wave or a quasi-square wave, it can come across this VAB voltages. In a similar way, if I now see this voltage, these two voltages here, okay, these two voltages uh, can also be a quasi square wave or a square wave, independent of how the left hand side bridge operates. Now, assuming that this transformer here is ideal, therefore this green colored voltage on the secondary will come across this inductor here. Okay, assuming that the transformer is perfect. So V1 by N1 will be equal to V2 by N2. And so we can see now that across this inductor, we are basically impressing two voltages. One voltage, suppose I give this name C and D here. One voltage VAB is it can be a square or a quasi square wave. In a similar way, C and D, that voltage will also be a square or a quasi square wave. So the underlying principle is that we have a controllable voltage across this inductor. That is what we understand, that across the inductor, we have a controllable voltage coming, right? Uh, so for example, here I can see that this voltage here, okay, is a square wave, and this voltage here, okay, is also another square wave. And in between, we have the inductor, right? So we basically have a very common and well-known circuit, uh, exactly similar to like a synchronous machines. We have two controllable voltage sources which are appearing across the inductor, right? So therefore, uh, power or energy can flow from the left hand side to the right hand side or right hand side to the left hand side. Okay, so if we can adjust the power flow by adjusting the phase shift, we can easily do that, right? And so this is the basic idea of how a DAB operates. By switching the left bridge and the right bridge, as I am showing now, basically you will get controllable voltage sources in these on the left side of the inductor and the right side of the inductor. And by manipulating these two voltages, we can actually allow the power to flow from left to right or right to left and many other things. Okay, so here this is what we have said, the auxiliary inductor. Therefore, this LK plays a major role in the operation of the DAB, in the sense that this uh, plays a major role because it facilitates the transfer of the bidirectional energy. Okay. It also reduces the DI/dt across the switching devices. And as we will see here sometime later, it will facilitate soft switching. Okay, we'll see this, all these things, right? So we understand that a DAB basically is working like two controllable voltage source uh, which are across the inductor LK. Okay. Now, so there are several ways by which we can actually make these controllable voltage sources. And the simplest of this is this called that single phase shift. But there are many other techniques like this ones. Okay. We will first understand this SPS, single phase shift, in details. If we understand it properly, then we will easily be able to understand all these three other techniques. So let us first understand what is this single phase shift technique. In this single phase shift technique, um, what we do is we always use diagonal switches in the two bridges. This means that we always use S1 and S4 or S2 and S3 together in the left hand side bridge. Similarly, we will use Q1 and Q4 or Q3 and Q2 on the right hand side bridge. Okay. However, so this means that the voltage here, okay, this voltage between these 2 points, which I have now indicating, the voltage here will be a square wave always. Okay, it will be square wave. Similarly, the voltage here on the right hand side, the output of the right hand side bridge, this will be also a square wave. Remember, VDC and V naught, these two magnitudes are different, okay, because there is a transformer in between. So there is a turns ratio of the transformer involved. So VDC and V naught will be different. However, both the left hand side and right hand side bridges are operating with square wave mode of operation. Okay. However, there is a phase shift. That is what I'm saying here. There is a phase shift between the two square waves. Okay. And that is why this is called as single phase shift. Okay. How does it look like? Let us see this one. We have given a detailed description. So here you can see there are this S1 and S2. Okay, S1 and S2 are of course complementary on the left bridge. And you can see here that S1 and S4 are given the pulses here. So S1 and S4 turns on here. Okay. Similarly, S2 and S3 turns on here. Okay. So which means that this VP voltage, right? VP voltage is this voltage here. This VP voltage is a square wave. You can see with square wave with VDC and minus VDC, which is coming across on the left hand side of the inductor. This voltage here, VP, okay, is coming there. In a similar way, if we see the right hand side, we will see that Q1 and Q4, like this one and this one, it is also given this pulse, right? Q1 and Q4. And again, Q2 and Q3 in a similar way, right? So then we will see that the VS voltage, okay, what is the VS voltage? This is the VS voltage. This is the voltage coming here. Now you can note here. So let me just erase this. Yeah. So if you see this VD, the VP and VS, okay, if you see that one, then you can see that there is a phase shift, right? There is a phase shift between VP and VS. Okay, there is a phase shift between the two square waves. Now, when VS gets reflected on the primary of the transformer, then V naught will become equal to V naught by N, right? V1 by N1 is equal to V2 by N2. So therefore, V naught voltage will become V naught by N on the right hand side of the inductor. So what is the voltage VL that comes across the inductor? Suppose this is the VL voltage. Okay, how does it look like? It is nothing but the difference of VP and VS by N. So we have now plotted this waveform, as you can see here. This waveform we have plotted here, right? So therefore, now the inductor current, okay, is going to act based on the voltage that is getting applied across the inductor and following the relation L di dt equal to VL. Okay, so this is exactly the inductor current will flow. And you can now understand that a replica of this inductor current is going to come from the input, and some part of this inductor current is also going to the output. So if we know the inductor current, we can also, because we have the switching states of the 4 switches, we can actually predict what will be the input current and what will be the output current of the 2 H bridges, right? Now, So suppose this left bridge and right bridge are given a phase shift of dTs by 2. Okay, so this is in seconds, but we can also express it in radian. Sometimes people express this shift in terms of radians. And so in radian, we can express this dTs by 2 as omega times dTs by 2, which means pi d. Okay, so we can express it in either radians or in microseconds or something like that. Okay, uh, so this is the relationship between the two, right? So suppose we have reached the steady state, and now we will analyze the operation here. Okay, so in this period from T0 to T1, in this period, we can see that the Vp is equal to Vdc and Vs during this time based on the switching combination. Okay, S1, S2, Q1, Q2. Based on this combination, we have this VL voltage coming here, the voltage across the inductor, where this is the VL voltage. Okay, this is the VL voltage, and it will be VDC plus V0 by N, because the actual voltage V0 is minus, so it gets reflected and gets subtracted. So VDC plus V0 by N. Now this voltage is, in this case, is positive, and so the current will rise. So let us assume that this current was here, okay, and the current has started to rise. Okay, I have taken deliberately the initial current to be negative. We will see, it doesn't matter. We will see that if the current is positive, what happens, like that. Let us start with a negative current. Okay, so you have this negative current which is flowing through IL. This means the current is actually flowing this way. Okay, it's a negative current. The positive direction of the current is taken as this way. Okay, this is the positive direction of the current. So this will be IL equal to positive. Okay, this is the positive direction of the current, this way, right? So in this case, IL is negative. Therefore, I have drawn the arrow in the opposite direction, right? Fine. So if this is the current, then of course, S1 and S4, although they are given pulses, but they will not conduct. The MOSFETs will not conduct. Rather, of course, the MOSFET can conduct. We have seen this because when we have when the channel of the MOSFET is formed, the MOSFET can actually conduct in both the directions. So yeah, but we have in this example, we have assumed that only the diodes are conducting. Okay, we have assumed that the MOSFET's internal resistance is much more than the diode, and so the diode is conducting. Okay, let us assume, because this analysis will then become true for IGBT based converter also. Okay, so let us assume that this is true. Okay, so therefore this IL current is negative, and therefore this D1 and D4 will be conducting, right? Now this current is going from right to left, as you can see here, and based on the dot polarity, you can see here there is a dot polarity given. So we know that if current enters through one dot terminal, current will leave through the other dot terminal. So which means that on the secondary side, the current will be flowing like this. Okay, so which indicates that this M2 and M3 will start to conduct. Okay, based on the direction of the current. Of course, again, you can see that Q2 and Q3 in the switch, M2 and M3 are conducting, assuming that the MOSFET is not conducting. Okay, so this is how the current will flow. Now, once the current reaches at this point, okay, at this junction, when the current is now becoming positive, okay, we are continuing with the same operation. You can see here we have from T0 to T2 during this entire time, there is no change in the switching state of the switches. So the current will go on increasing, and at one point of time, it will become positive from negative. Okay, so it will transition. It will have a transition, and it will continue to rise with the same slope as before, because here the voltage that is getting applied across the inductor is so much, and that is causing the current to go high. But as soon as the current changes the direction, now you can see the current has become this way and this way. Okay. As soon as it does, then what happens? The diodes on the left and right hand bridges, they will no longer conduct anymore. And so now S1 and S4, the MOSFETs S1 and S4, and on the right hand side, the MOSFETs Q2 and Q3, they will start to conduct. And you can trace the direction of the current by following the figure. Okay, so this is what will happen when the transition happens. So one thing to observe here is that when S1 and S4 as well as Q3 and Q2 are turning on, which is at this point here, okay, just when the current is going from negative to positive, right, the voltage across all the MOSFETs are zero. Why? Because the diodes were conducting already. So which means that in an ideal case, the voltage across the MOSFET when it was turning on is almost negligible. Okay, it's zero ideally, but in practice it will be almost like zero, right? So therefore, when the switches, these four switches S1, S4, and Q3, Q2 are turning on, they are turning on at zero voltages. And that is why this is called zero voltage switching of the MOSFETs. Okay, this is zero voltage ZVS at turn on. Of course, this will help in reducing the switching losses, because if the voltage across the device is zero when it is turning on, then ideally we have zero switching loss. Okay, because the switching loss is proportional to the instantaneous voltage across the MOSFET and the instantaneous current through the MOSFET. Okay, in this case, even the current through the MOSFET is also almost zero. Okay, so therefore, the losses in this MOSFET is almost zero. Okay, so this is something which is called ZVS. Okay, zero voltage switching at turn on of the MOSFET. Okay, and this can substantially reduce the switching losses. So now we can see what is the current, okay, during this time. Okay, and you can see here that the same voltage is getting applied to the inductor. And so we can uh, write down the equation of the current with initial and final values. Let us give these values as IL0 and IL1, okay, as I have shown it here. Okay, IL0 and IL1 and VDC plus V0 by N dTs divided by 2L. Okay, so yeah. Now in this one, now in the next interval, okay, from T2 to T3, okay, what will happen now when at T2, what is changing is that we are changing the right hand side bridge pulses. Okay, now instead of Q1, previously Q2 was on, now Q1 is turned on. Okay, so Q1 and Q4 are given gate pulses. Okay, now the current is still positive. Okay, so the current was flowing like this, and this current was flowing like this here. And as soon as you give the pulses to Q1 and Q4, Assuming that the MOSFET is not conducting, we will see that the diodes M1 and M4 will be turning on. Okay, assuming again that the channel of the MOSFET is not able to conduct anything at all. So M1 and M4 will be conducting, right? Now the equation, what will be the equation? Now, as soon as this conducts, okay, M1 and M4, note that the voltage across this point here will become V naught, okay? And now the voltage across the inductor will change to VDC minus V naught by N. Earlier it was VDC plus V naught by N. Now it will become VDC minus V naught by N. So then, since the voltage across the inductor has now decreased in this one, so the slope of the current as expected, the slope of the current which is shown here, the slope of the current will decrease. The equation during this time is given by this expression. Okay, it's the same thing, following the same principle. Okay, so this is how the second interval T2 to T3 will happen, right? Now, at the next interval comes, and in this interval, which is between T3 and T4, what we do here is that we change the pulses of S1, S2. Now you can see here, this is the transition happening at this point. Okay, so the primary voltage is changing from VDC to minus VDC, right? And so the voltage across the inductor, okay, is becoming negative, right? So which means now the inductor current will start to fall. Okay, it will start to fall like this. So the you can see here S2 and S3 are turned on. Okay, and a negative voltage will appear in this case, okay, across the inductor. And as soon as this happens, the current is still positive. So which means the current will now flow like this, okay, D2, and it will go like this, go like this, and then it will go like this. This is how the current will flow. Correct. So D2 and D3 on the primary side will be conducting, and the current on the secondary side is still like this, and therefore M1 and like this and M4 will be conducting, right? So D1, D2, D3, M1, M4 will conduct. Again, we will see that there will be a transition, okay? And this transition is from T4 to T5. And then again, what will happen is uh, as the current reverses, Q1 and Q4 will turn on. Okay. So this is how the conduction happen. So here also you will see that the Q1 and Q4, they are now turning on at 0 voltage, because Q1 and Q4 earlier M1 and M4 were conducting, and now the current changes from M1, M4 to Q1 and Q4. And so all four switching transitions, okay, are at ZVS turn on for both the bridges. Okay, you can see this one, okay, here. So this is basically what is the ZVS turn on of the MOSFET, of the DAB. Okay. Uh, and next we have this interval T5 to T6, and there again S2, S3, M2 and M3 will conduct, and you can follow this by checking this one. Okay, by checking this one. So we find out, we understand that basically you can understand that there are 4 switches on the left bridge and 4 switches on the right bridge. So there are total 8 switches, right? This you understand. So each switch can have a turn on and a turn off. So there will be total 8 into 2 equal to 16 switching transitions. Okay. And out of this 16 switching transitions, this particular DAB, the operation that I showed, had 8 transitions with ZVS at turn on. Okay. So you can see here 8 into 2, 16. There are total 16 transitions because there are 8 switches. And out of these 16 switching transitions, 8 switching transitions are soft switched. Okay. Which means that the losses here are substantially low. This is one of the very desirable features of dual active bridge. Because of this soft switching feature, the efficiency of dual active bridge is actually pretty high. So very often we see dual active bridges with reported efficiency of more than 98%. Very often. So therefore, this soft switching feature of the DAB must be preserved at most of the operating conditions, because that is where the benefit of this converter will emerge. So therefore, we will see the soft switching part in details. But here you can understand that 8 out of 16 switching transitions are now soft switched. Okay. In some other versions of the DAB, for example, we also have other versions of DAB, like this L will, there are circuits in which this L is replaced by an LC resonant circuit. Okay, this we will not discuss here in this lecture, but it is possible to have a resonant circuit here, okay, instead of the L. Some academic and commercial implementations have this. So then what happens is that there is this voltage here is a DC voltage, but the current that flows here is no longer the current waveform that I have shown. So the current will become something like a sine wave. Okay, because it is resonating, so it will resonate and the current will increase in a sinusoidal fashion and ultimately come to the zero crossing. So now what we can do is, along with this ZVS, we can also have zero current transitions, ZCS. Okay, so there is also something called as ZCS, zero current switching. Okay, so along with ZVS, we can actually have also ZVS, ZCS and ZVS together. And in that way, actually, there are reported that 12 out of 16 transitions have been made soft switched. Okay, so this is something extremely desirable because this converter is going to be switching at say 50, 60 kilohertz and transferring a lot of power. We have seen this one. And this kind of soft switching inside the converter, either through a simple L or through a LC resonant circuit, these are very desirable features of the converter. Okay, and so the efficiency can go up drastically. We will not talk about the ZCS in this part of the course, but I just wanted to highlight that it is possible to have the, instead of L, we can also have a LC circuit, okay, instead of the L simple inductor here. Now let us come back to our discussion with the L only. Okay, so we have now seen how the inductor current behaves, right? So IL0 is here, IL1 here, IL2 here. So we are giving different names. And because at steady state, the waveform must be symmetric, half wave symmetric. So then IL2 will be equal to minus IL0. So IL2, this value here is minus IL0, correct? So if you do like that, and then you can, then these equations, you can find it out, right? Because we have seen these equations, how the, like this one, these equations, okay, you can solve, right, with this one, assuming that IL2 is equal to minus IL0. Okay, when you put these equations, expressions into those equations which we have already seen, we get to this values. Okay, IL2, IL1, and IL0. These values are important from the transition point of view, exactly where the transition will happen. But more importantly, it will give us the average values of input and output currents. So, for example, the input current waveform is now shown. Okay, this red one here, this is the input current waveform. Why is it something like this? You can understand from the switching point of view. For example, IL, the inductor current is same as I in when S1 and S4 are conducting, right? So therefore, when S1 and S4 are conducting during this interval, right, we have drawn I in. This is the red colored is the I in. I in is exactly following IL1. On the other hand, when S2 and S3 are conducting during this interval here, we can see that I, because S2 and S3 are conducting these two diagonal switches. Therefore, I in is equal to minus of IL. And so here, this part of the waveform from T3 to T6, this part of the waveform is minus of the inductor current. Okay. And so this is drawn here, this in I in current. Okay, we can draw it like this way. So we have not shown it, but the average value of this input current, if we do it properly, it will be something like this. Okay, you can do it yourself. We are not deriving this here. Okay, but if you just put it, the area under this curve, okay, it's half base into RT, because you can make it triangular shapes, trapezoidal shapes like that, and can get the average inductor current, okay, or average input current in this case. Okay, in a similar way, the output current can also be derived, right? Because if you know this inductor current, you will also know the secondary current. And if you know the secondary switching states of all these four switches, then similarly, we can also find out what is the I naught current. And so this I naught current, this green one, this is shown here. Okay, this is the current. And in a similar way, we can find out the um I naught like this way. Okay, Ts by 2 ln d into 1 minus d VDC. If I know the output current, we will also know what is the output power, because output power is nothing but V0 times I naught. Okay, V naught times I naught is the output power, right? So if I write it in a proper way, P out is equal to Ts by 2 ln d into 1 minus mod d into VDC into V naught. This mod d was not shown here. Actually, this expression here is mod d. Okay, it was not shown here in this expression because we were following the diagrams. Okay, but when the note that the d, the duty ratio, can be positive or negative. Okay, what is positive d? Positive d means the q1 and q2 are lagging, so this is the positive d. Okay, so this is where d is plus d. But if you, on the other hand, make Q1 and Q2 the other way, so if Q1 and Q4, this one becomes, he comes here, Okay, and it starts to lead S1, S4 combination. Here, Q1, Q4 is lagging S1, S4 pulse. But it can happen that Q1, Q4 is leading the S1, S4 pulse. Then D will become minus D. Okay, you can make it the other way. That is why we have not made the expression complicated, but this is the correct expression. Okay, this is the correct expression where P naught, P out is ds by 2ln d into 1 minus mod d into VDC into V0. Okay, so this is basically V naught into I naught. Okay, and this expression shows us something. What it shows is that, first of all, power can be controlled with respect to D, okay, the duty ratio. This is very evident. It increases to a maximum value of power, okay, and that is possible when D is equal to 0.5 or the phase shift is pi by 2, okay. So at the pi by 2, what does this mean? That the what it means that this S1, S4 was here, okay, and Q1 and Q4 are 90° to that. Okay, so this one was Q1, Q4 pulse. Okay, so and this angle is 90 pi by 2 radian. Okay, this is the delay. But if you make Q1, Q4 leading, it's also possible, right? And then this phi will become minus pi by 2 if it make reading. So this is shown here. Okay, you can make it this way. So then what happens is, let me draw it. Then Q1 and Q4 probably will become like this. Okay, Q1 and Q4. Okay, and then from this point this way, so phi equal to minus pi by 2 leading, right? So we can now see that this is a very versatile converter, because if you make the switching of S1 and S4, you can make it lagging or leading with respect to each other. And then the power can be made to flow from the left hand side to right hand side, or from right hand side to left hand side. Okay, remember that this side can be an EV battery, okay, and this side comes from the grid, okay, that you should remember. So just by simply changing this duty ratio between the two H bridges, I can control the power to flow from grid to battery or from battery to grid, okay. And the relationship is also quite easy to understand and easy to implement. Okay, so this is one of the advantages of the DAB, because here seamlessly it is possible to exchange power from left to right or right to left. Okay, uh, so yeah. So the input power now we have plotted. Okay, there is something else which is also interesting to observe. Okay, so this is the input power we have now plotted for a value of where D is positive. Okay, now note this instantaneous value of power where we see that there are some yellow parts. Okay, okay, these yellow parts are the problematic parts. Why? Because when the D is positive, we want power to be flown from left to right. We want the power to flow from left to right bridge. This is what we desire. And that is why the average value of this power is positive. This is what we want. See, average is positive. Right? However, at some parts of the waveform, particularly these yellow parts, right? The yellow parts, we have the negative instantaneous power, and that is coming because this inductor current is this part, and if you see, if you multiply, okay, these parts, okay, then these yellow parts are coming, right? And we want, of course, when we want to send power from left to right hand side, we do not want any power to go back from right to left, but this is exactly happening. Okay, so there are some parts where the power is negative. This is also called the backflow power and the reactive power. Of course, this is not at all desirable. So this is one of the drawbacks of this single phase shift. Okay, the backflow power is very high in single phase shift operation. Okay, this is something to be noted. Uh, Also, you can see that if we see the current, okay, IL2 expression, we will, if you manipulate the expression, we will see that as the value of D increases, this peak current, so this is the IL2, okay, this current is the IL2. This current's value will go on increasing. So it will become more and more peaky. So generally, we keep, we do not go up to 0.5. D equal to 0.5 is rarely used. Generally, up to D equal to 0.4 is recommended. Okay, we do not go beyond that because then this peaky of current, peakiness of the current, and from also from a little bit from the control point of view also. So we keep the D max like close to 0.4. Okay, maximum. Okay, now there is the other part of the DA. So we now understand the operation of the converter. We also understand the input and output power and how they are. There is also in SPS modulation, there is also an instantaneous back power. We understand this one. Now we will go a little bit inside the ZVS operation of the DAB. Now let us recap this circuit which we had earlier shown. In many of the DABs, you have a stage one, which is AC to DC, right? And you have a DC link capacitor. And then basically it is a DC-DC converter with an isolation. This is what the DAB is. Now, note that this capacitor, we want to make the size, this is an electrolytic capacitor. We want to make the size of this capacitor small. Okay. If we make this, because we want to make a compact converter, if we make the size of the capacitor smaller and smaller, what we will observe is that on the input voltage, we will see an second harmonic oscillation coming. Okay, in particular, when it is a single phase operation, this second harmonic oscillation or a ripple on the capacitor voltage will appear. So here you can see this is the V in voltage and there is a ripple. Okay, there's a ripple in this voltage because we have reduced the capacitor to substantially. But we want and the output voltage to be constant. Okay, so this means that the gain of the converter, okay, the gain of the converter must be varying throughout, because the gain of the converter we can say like output voltage by input voltage, it must be varied continuously because we want a stiff output voltage. This is also true if the DAB is fed from a diode bridge rectifier. Okay, so input voltage will fluctuate. Okay, in a diode bridge rectifier, we know the input voltage fluctuates. So under this fluctuating voltage, the DAB may not work in ZVS. Okay, this is what we will show now. As I told you, one of the advantageous features of the DAB is it operates automatically in ZVS. But we do not want to lose this feature of the DAB. Okay, so DAB may not also work in ZVS if the power output becomes very low. So we will see this and how we can actually do this thing. So yeah, so the input or sometimes the input or the output bridges together or individually work out of ZVS. They do not follow the ZVS. Okay. So first let us define what is the gain. Gain is equal to V0 by N times VDC. Okay, this is how we define the gain of this converter. G is usually 1, but if the voltage is fluctuating, as I was showing previous slide, the input voltage may be fluctuating, then the G can be more or less than 1. Okay, instantaneously the G value is changing. What happens if such a thing happens? Okay, now let us first take a condition which is the normal condition. Okay, and suppose we will take this condition and the waveforms are shown. This waveform we have already seen. Here is the red colored waveform is this waveform, and IL by N, the secondary side waveform is the blue one. Okay, so in this case you can see here that when S1 is turning on, S1 is turning on here. Okay, this is where S1 is turning on. The um, D1 and D4, this is where the S1 and S4 pulses were given, but at this point D1 and D4 were conducting. So when this transition happens, at this point here S1 and S4 starts to conduct. Okay, actually, and during that time D1 was already conducting. So it transitions from D1 to S1. In a similar way, when Q1 is turning on, okay, so you can see it here, when Q1 is turning on at this point, M1 was already conducting. So we have the ZVS on both the sides. Now, suppose the output power reduces. Okay, the output power reduces means now the phase shift is reduced. Earlier, you see this much of phase shift was there. Now the phase shift is reduced because depending on the phase shift, we can change the output power. P is directly proportional to D into 1 minus mod D, which means power is directly proportional to the phase shift. So I have now, suppose the load is changing and I have reduced the phase shift, right? What happens here is that the ZVS will happen in the primary, but ZVS will not happen on the secondary. Why will it be so? When phi is reduced, you see here the current was here, from which the current goes like this here. Okay, see here S1 and S4 are given pulses, but D1 and D4 will continue to conduct up to this point. Okay, and then S1 and S4 will take over from here. So ZVS is happening on the left bridge, no issues about it. But what happens to the right hand side bridge? In the right hand side bridge, Q1 and Q4 are given pulses at this instant of time. Okay, at this instant of time, okay, this current, okay, this current was flowing like, okay, this current was in this direction. The current is negative, so which means this is the current. Okay, so here you can see that Q1 and Q4 are turning on because I have given pulses here, Q1 and Q4, right? So Q1 and Q4, when they are conducting, just before that, M2 and M3 were conducting. So M2 and M3, they were conducting because the current direction was like this. And immediately it switches from M2, M3 to directly to the opposite Q1 and Q4. Okay, the top, from the bottom to the top switch, it transfers. So this is basically hard switching, right? because the voltage across Q1 was the full DC length and it must go to 0 now. So therefore, this transition here, this transition for the right hand side bridge is hard switching. Okay. So basically the reason is IL1 by N, this magnitude of the current IL1 by N is less than 0. That is why this is happening. Okay, in Q1, Q4, right? So we can say that if we want to avoid such a situation, we must make sure that IL1, this condition must hold true. So this value IL1 by N, that value should be greater than 0. Okay, if we want to avoid such a condition. So if you do the manipulation, you will find that D must be greater than 1 minus G by 2 for ZVS to occur. Okay, this is a necessary condition for the ZVS to occur. So we can say that now we can plot the variation. Okay, so this region here is no ZVS. We will avoid this region of operation because this is hard switching. Okay, we will try to operate inside the ZVS region. Of course, so from this equation we have plotted, D should be greater than 1 minus G by 2 for ZVS to occur. So this is this region. D is greater than 1 minus G by 2. Okay. One thing is that if G equal to 1, right? If G equal to 1, we say that ZVS is always ensured. But under some condition, we will see that there is so we are operating in the ZVS region, and under some condition, we may go into non-ZVS region or the hard switching region, and thereby reducing the efficiency. Why will it happen? Suppose we are operating here, okay, on this line, okay, our gain is 0.7 and we have a power which is corresponding to this one, P equal to say 5 kilowatt. Okay. Now we want to, and the gain is 0.7. Gain is coming from the voltage gain and the power is 5 kilowatt. Suppose. Now, after some time, the power becomes 500 watt. What will happen? From this point, with the same gain, because the voltages are same, we will move to this region here. This region may be P equal to 500 watt. You can see the power is directly proportional to D. Remember, power is directly proportional to D into 1 minus mod D that we have shown. So we will therefore from this value of power, we will move into P equal to 500 watt power region. And thereby we will move into this particular region where this is hard switching. We should try to avoid that one. Okay. So with this G equal to 0.7, we will be sometimes there is a chance that we may move into the non-ZVS operation and hence reducing the efficiency. Now, take the other condition. Suppose G equal to V naught divided by N VDC, which is now greater than 1. Okay. So then V naught by N is greater than VDC. And again, we can draw the voltage and current waveforms with the power if it reduces. Okay, then you can do a similar analysis. I'm not doing it here. You can follow these curves here. ZVS will happen in the secondary or the right hand side bridge. So ZVS will happen here and hard switching will happen here. Okay, you will see, you can follow the conductions of these diodes and the transistors. Okay, and you can find out, you will see that this condition holds, right? So therefore, similarly, we will say that IL2 is this one must be greater than 0 for the ZVS to occur in primary. Okay, So D equal to D greater than G minus 1 by 2G is necessary condition for the ZVS to occur in the primary. Okay. So therefore, we will now see the non-ZVS and the ZVS operations. And then we can plot the two areas. Okay. So combining both the plots for G more than 1 and for G less than 1, okay, we see that such a condition or such a plot happens. In this area, the secondary side is hard switched, and in this area, the primary side is hard switched. Okay, and we would like to avoid both these hard switching areas, and therefore we will say that we should operate in this region given by this boundaries. Okay, this is the region here. Okay, we should operate so that we are always in soft switched area. Okay, fine. Now, one thing to note, as I told you, the value of gain, okay, the value of gain is not constant. The value of gain is going like this. So we can say that the lower value of gain is 0.7 and the higher value of gain is say 1.3. So the gain is fluctuating. The gain is fluctuating. So that's why I have drawn these two pink lines here. Okay. So the DAB is operating between these two gains of the between these two voltage gains. So this is the voltage gain dependent on the input and output voltages. But power is independent of these two voltages, right? Whatever power we want to set. So suppose we say that we are running with a power which is corresponding to this blue line. So corresponding to this D equal to 0.25, we may say that we are going to run at this point. Okay. Now, what, um, why have we chosen here? There's a reason for this. I can also go for a higher value of D max. I can go on this line. Okay. It will give me greater power operation. And if I move, this line moves this side, there is more chance that I will be in the soft switch region because this unshaded part, I will move more into that. But remember that if you increase the value of D too much, then it increases the backflow power, that YOLO region, which I had shown earlier, and it will reduce the efficiency. Okay. So this is one drawback. Okay. One challenge that we have if the D value is going to be very high. On the other hand, if you see the other side challenge, if you move the value of D lower, suppose you move the value D here, okay, for the same, then what will happen? Of course, if you move it the D here, then you are going for lower power flow, which means you are not utilizing your converter fully, right? So not utilization of the converter, but also there is a chance of hard switching because you are now moving more and more towards the hard switching area. So therefore, a designer always has to make a compromise on how he will kind of like where will he place the value of D? Okay, where is the optimum placement of the value of D or the phase shift so that he avoids the hard switching area. At the same time, he doesn't increase the backflow power also. Okay, so both these conditions have to be kept in mind. Now, there are other modified SPS techniques. Now we will touch upon them. Okay, which can actually provide higher soft switching areas. Okay, so for example, let us see this one. Okay, basically it is very easy to understand. Uh, the other second one is called the EPS. What is EPS? EPS means extended phase shift mode of operation. Okay, what we do here, um, In this technique, one of the bridges work with 50% duty, while the other may work at 50% and may not work with this 50%. So suppose the right bridge is working with 50%. Okay, this means that this side's voltage here, this is a square wave. Okay, but this side, we have a phase shift between D1 and D4. So let us see this one. You can see here, if we have a phase shift between D1 and D4, so here you can see S1 to S4, these pulses, there is a phase shift. Okay, we are no longer switching the diagonal switches all the time, right? So then what will happen is, then Vp is no longer a square wave, right? Vp becomes a quasi square wave. You can see here, there's a zeroed period coming here. This is coming because at some point of time, two upper switches or two lower switches are turned on simultaneously. So therefore, Vp will become a quasi square wave. Quasi square. It is no longer a square wave. Whereas Vs is a square wave as before. What is the impact of this one? The impact is that the V8 VL voltage becomes more staggered. Okay, and several steps are there. Okay, you can see here these different types of steps are coming into the VL voltage. What it indicates is that this current IL is now there are two things. One is that the shape of IL can be controlled. Okay, so this shape is now modifying. It is getting modified. Okay, there are more corners now because there are more steps in this voltage. So there are more corners, and these corners of the current are adjustable. Okay, so this is one thing that we observe. So we can actually wave shape the inductor current. Okay, we can shape it as per our wish. But the other thing which comes as a consequence of this shaping is that the input power, you can see under certain condition, the input power is zero. And under certain condition, the YOLO region, which was earlier shown, that region has drastically reduced. This is very important. By wave shaping the inductor current, which again comes from the shaping of the uh, inductor voltage, what we have done is we have basically reduced dramatically this um, negative power or feedback power, the reactive power, whatever we say, the power which is going back, that power we have changed. Okay. So during the zero voltage period, inductor current circulates within the switch. Of course, there is a zero voltage. So in the zero voltage, this current will be flowing like this. Okay. And the input current is zero. Power drawn from the input is also zero. Yeah. You can see here, this power is also zero, right? And so the back power flow region reduces, and therefore the efficiency will be more in this extended phase shift technique. But one drawback here is that we are not utilizing the full capacity of the converter. Remember, we are not taking any input power. Okay, we are taking zero input power from the left hand side during this part. So we are increasing, but we have reduced the backflow power. So basically, we have increased the efficiency of the converter, but we accept that we are not utilizing the full capacity of the converter. Okay, there are some zero parts in the P in. Okay, so this is something which is interesting. So the rate of rise, so we can also say that the inductor current, the rate of rise is smaller and the peak value of the inductor current reduces. Okay, all these factors we can see. And so this reduces the conduction loss and the current stress on the switches. Of course, this inductor value, we will show you an example later that these peak values, we are now shaping the peak values. We can reduce these values. And so the stress on the switch and the conduction losses, all these things can be changed. Okay, so these things can happen. Okay, so similarly, we can also say that we can have a dual phase shift. Okay, and in this case, what happens is there are three phase shifts, but the phase shift within the left bridge is same as that with the right bridge. Okay, so there are two control variables which we are saying D1 and D2. Okay, so basically here you can see that we are now producing two quasi-square waves, but the D1 here and D1 here are the same, but D2 is variable. Okay, and so similarly we can also get a different shape of VL. Okay, and therefore we can wave shape out the inductor current. Okay, with this condition. So basically, both the bridges provide a zero period. That is, both the bridges have phase shifts, and we can provide lower peak current or reduced current stress. Okay, we can do this way. And the most general case is the triple phase shift. Okay, where basically we do not put any restriction, and this side waveform is a quasi-square wave, and this side waveform is also quasi-square wave without any restriction on what are the uh, no restriction in terms of the duty ratios. So there are three control variables, and both the bridges may work with unequal duty ratio. So with this many number of control variables, the control complexity also increases. Okay, that one has to keep in mind. Okay, so TPS is the more general mode of conduction, and other modes are basically subsets of this TPS conduction. So basically what we do is we are basically varying the degree of quasiness of the input and output voltages. This is something to note. We are modifying, as you can understand, you see this waveform is how we have introduced the notches in this waveform as compared to the SPS. Okay, in SPS we had two square waves and we just adjusted the phase shift. But now inside these square waves, we are shaping by introducing this quasiness. Okay, this is what we say, that by the varying the degree of quasiness, the inductor wave shape can be modified, and the power transfer capability will also change. So this is the power versus D. Okay, in this is the SPS control, and then we go to EPS control, and then we go to DPS control. You can see that the regions are getting changed. Okay, this is something which is interesting to note. Okay, that a variety of, so the power, so you can actually have, for this value of P, you can have several values of D1, D2 coming up. Okay, so along with the power, you can have a lot of optimization, efficiency maximization, current stress minimization, okay, ZVS even at low power. So there are a lot of literatures available on the use of different types of EPS, DPS, TPS, SPS control. SPS is only single. All these types of control and what we want to optimize. Not everything is good in one control. Some things are good in one control, some things are good in other type of control. So hybrid controls are also possible. So there is a lot of literature available for this kind of thing. So here we will show you some simple simulation waveforms, right? So here, this is the primary and the secondary bridge, and you can see the phase shift here, which we are given. And this is the VL voltage and how the inductor current looks like. But suppose you have introduced an EPS, where you see there is, we have used a quasiness in the primary. And then, of course, the VL waveform changes. And now you see the inductor current, right? The inductor current shape has changed from the previous one, right? And then you have the DPS. So you have introduced the same quasiness in both these converters, but there is a phase shift between the primary and the secondary, and the inductor waveform has been modified. And lastly, you have the TPS one, like this waveform, okay, this condition. Now, suppose you compare SPS with EPS. Okay. Suppose we are running with this condition, 300 watt output, 48 volt input, 150 output, and this is the inductor, and these are the capacitors, and switching frequency of 30 kilohertz. Now, both the cases, the power have been kept constant. Okay, here you can see the power is kept constant, and output and input voltages are also kept constant. So it's the same converter. Okay, but now we are going to compare SPS with EPS. Okay, so if you see the inductor current in SPS and the inductor current in EPS mode, this is the inductor current here. And here the peak is 43 ampere. Okay, RMS is 23, like that. Okay, um, and of course the inductor current peak 43 means the input current peak is also 43, right? And the mean is 6.25. But on the other hand, if you see the EPS mode, right, the peak current has reduced to 31. You compare this with 43. Okay, so the peak current you can see here has reduced to 31 ampere. Of course, the RMS current has decreased to 12.2, right? So, but the mean current remains the same because we are sending the same power in both SPS and EPS. But you see the advantage of going to EPS mode, where this peak current of 43 is going down to 31 ampere. So this is what happens by wave shaping of the inductor current. That is where the different modulation techniques actually come in handy. Okay, and in case of SPS, the average backflow power is 320 watt, which drastically reduces to 32 watt in case of EPS mode. Okay, so these are something which we can note. Okay, so we have made some of these DABs in our labs also. So these are some of the data which one of the students made here. And these are some experimental results. And efficiency, we have also obtained an efficiency in a lab prototype, okay, with this kind of losses. We have obtained a very good efficiency also, 98, more than 98, okay. So these are some of the references which you can look into. There are a lot of references for DAB. One of the first references is the paper by Professor Didonker. This paper at the top here. This is one of the most important papers. And DAB started from there. And so this is basically, so what we, in summary, if we summarize what we have learned, is that we have learned the basic operation of the DAB, and it is considered to be one of the most important converters for future. It's an isolated DC-DC converter, and you can control both the output voltage and the output power, input power, because it is bidirectional by nature, and it has an isolation in between. So this is one of the most promising converters for the future, okay, for useful for EV applications in particular. With this, we end the lecture on DAB.